continuous integration. It's constantly building. It's making sure someone hasn't checked in something that's failing things. It does a whole ton of stuff too. It has Docker plugins, but if you think of Spinnaker kind of wrapping Jenkins as, and that build phase would be just one stage, within these pipelines. So if you see that I think there's like 2 or 3 videos out there that actually show these pipelines at full speed, and it's there's like multiple of them going on at once and building in separate regions, right? So yeah, all these things are tied together with Spinnaker. So pretty cool stuff there. Infrastructure. Yeah, here's kind of a global view. But yeah, like the real meat here is these pipelines, which of course are not working right now. So yeah, a lot of people, there's actually first-class Kubernetes support for
really output a tensor. It just outputs a handle to the data that it has, right? So that's the basic idea of tensors, right? So all of these are operations, and they won't run until you put a session in it, right? So like I said before, we have these 2 arrays that we're defining in NumPy, and then using this TensorFlow add operation to add them together. But when you run it, you'll see it doesn't output the addition of these 2. We have to wait until we run it. So we start up a session, and then we actually run that.
So how do you print out the result? Now without rerun it again. So if I print C, it only prints out the mapping information of the C, not the result.
Yeah, so what you can do is, instead of just doing session.run, you can actually store the C result, right, as its own output. So we do run C. This should probably go after.
Okay, so I'm going to create a new variable.
Yeah, so basically you can, when you output it to a Python variable, it actually converts that that TensorFlow tensor object, the numeric output, it converts it into a NumPy array. So then you can take your TensorFlow output and start manipulating it in SciPy and all the other libraries that you might want, matplotlib, etc. So you can just get a handle to it and then start working with it again, and then you can print it out the same way you would with NumPy arrays. And in this example, I'm just printing out the result of the session and not getting a handle of it. Great. So now most operations have a name parameter that you can pass in. This is useful for a number of reasons. One, you can see it in TensorBoard and it will give the specific name. You can also, it also allows you to pull in nodes directly from their name. So we had a question about, well, what happens if you just add a placeholder without assigning it to a Python variable? Well, if you don't give it a name, right, if you don't know its name, then it's just sort of lost in the ether. You can get a list of those operations and then say get operation with its name there. But if you already know its operation, then you can say, hey, TensorFlow, can you please find this operation that is there and give me a handle to it? I accidentally lost my handle to that node. So names are really useful. I recommend whenever you're setting up operations to add names. Okay, so we have this graph object. Before, it just sort of existed in the ether, and we didn't explicitly talk about it until we saw the session writer, where we said, hey, writer, can you please, for the graph, can you use the session.graph object, right? All the way back up in the first example. So TensorFlow has a graph class, right, that it uses to contain and hold on to the different operations that we're dealing with. But you can, if you don't define one and you just decide to use start typing in operations, it's going to use the so-called default graph. But when you start up TensorFlow, it just starts a graph for you so that you don't have to necessarily explicitly define a graph. But you can have multiple graphs and run, like, basically define them in the same file, and then have different sessions running those different graphs. So you can create a new graph simply by just saying TensorFlow.graph and assign a handle with it here. And then if you want to, yes, sir?
So are constants shared between sessions also?
So no. So the way it works is that every operation is going to be placed in a specific graph. right? So when you're, if you just, let's just, as an example, so if we had a tf dot, should do something, if we had a constant here that was just a tf dot constant, right? Right. So we just had this constant of 4 here. This, right now, there's this sort of imaginary default graph, right? It's not imaginary, it's real. It's this invisible default graph space, right? So this constant is placed in this in the default graph. Now, if we use the width command and create a width block with our graph, that's what this is, with our new graph as default, we can actually create a different constant that is now attached to this new graph. So we can say other is equal to tf.constant 6, right? So we can actually see an example of this, right? So the way, I'm going to insert a new cell below so we can actually see what's going on. So when you, so we have this default graph, this implicit default graph, and now we have our new graph. When you start a session, you need to define what graph you're using. If you don't define a graph, it's going to automatically assume you want the default graph. These are all just sort of syntactic sugar that's included. You can actually get the default graph, which I explained down here, right? So this, if I run this command, right, our default graph is now held with default graph instead of our new graph. Can I include this here? So in any case, we can show off the difference here. So if we start a new session, let me say session is equal to tf.session. We can actually, if you can do this, you can say, hey, instead of doing the default, we're going to say our graph is equal to new graph. Okay? And then what we can do is actually say session.run other co. And I know that it's like, well, we obviously pointed to this one. Like, that's not fair. But you can see it's 6. And I believe if I just do this, this should result in an error because it's not in the graph. Right? Does that make sense? So if we wanted to get this constant, what we could do, I'm going to close out this guy. Close him out. What we can do is instead, we can either put in no graph because we're just putting in the default graph, or we can say explicitly graph is going to equal the get default graph object here. So this will return a handle to the default graph. And then we can actually run the ses.run co, and this should return 4. Boom. So, yes?
What's the relationship between second and graph? Is that one-to-one, one-to-many, or?
So it's one session to one graph, one graph to one. Each session can have one graph. Each graph can be hosted on many sessions. Oh, did I get that right? Yeah. So a graph can be you can define a graph and then start multiple sessions and train them separately. The reason that this is doable is that you can have variables, and in the various variables, the location of them is placed in the graph definition, but the actual value of them is actually in control of the session itself, and we'll see some of that below. The basic idea is that, and you'll see that when we do this variable initialization, the session itself has to initialize its own variables because it's in charge of the value of variables. Variables being what will be weights. In any case, don't want to get too bogged down in that. Basically, you have a default graph. You can, by default, obviously, but you can also create your own new graphs and define them separately. And you can run those new graphs by passing them into your session. So you can also, another important thing about this tf.get default graph, it is actually in scope. So when you use with new graph.asDefault, it will actually set that as the new default graph. That's what the with command does. So if I run this.
Yeah, just to kind of, he asked kind of part of my question. So, so the scope, basically the scope of any constant is to a graph.
Yes.
And whenever you write a constant, another way, can I think of the default graph as kind of like the active graph?
Yes.
So, right. So basically, whatever is the active graph, when I instantiate a constant, that's the graph that's going to get assigned to.
Yes. There's also a way to explicitly add operation. You can, with your graph, there's an add operation method, but that's just not nice. But just to prove the point, you can say is it. So this should print out true the first time, false the second time, because inside this scope, new graph is the default. But outside, once we exit this with block, we are saying, hey, okay, we're done with new graph being default. We're going to go back to the global default, and there's always a global default there. Cool, great. So that's graphs. Let's move on to sessions. Like I said before, like we've been using them. They're what's in charge of actually running the graphs. They need to have a graph specified. There's a target parameter that is mainly used for distributed TensorFlow, which we're not going to be talking about today. It's just a lot. It's very complicated to be able to set those up efficiently, properly. There's also a config option, which allows you to specify more detailed information about logging information about GPU placement and all that. But for the most part, when you're starting a session, you're either going to put in nothing or just a graph until you start getting more and more complicated things going on. But for basic use, this is what you're going to be dealing with. So like I said before, we have a default graph session. You can also enter in a session with a new graph. Then we have our running sessions. You do that with sessions.run, like I said before. The value that you want to pass in is a fetches, right? And that is what you pass into fetches is a list or a single value of operation handles that you want to run. So basically you say, hey, TensorFlow session, hey session, I have this cool graph, you're in charge of this cool graph, can you please run it for me? And this isn't best practice, you probably shouldn't be doing like addition operations inside of here, but because it works from inside out, this will be added to the graph before this session tries to run it. So if I do that, we'll get 5. Great. You'll see more of these sort of do session.run on just a singleton operation for sort of one-off initialization operations. We can also, like I said before, we can also pass in our feed dictionary. Those are the inputs that we talked about before. This is just more expounding on that same idea. And like was asked before, TensorFlow, you absolutely must have, you must pass in information for a placeholder if that placeholder is needed to calculate your output value. So if you try to do this, it's going to print, you're going to get an error, right? If you try to run a placeholder, like run these 2 nodes, if you try to run B, which depends on this placeholder without passing in, you're going to get an error. So what you need to do is create a feed dictionary for that placeholder, and then it works. Hooray. And then we'll just close these guys out. So those are sessions. Any questions about sessions? Great. Again, I know I'm speeding through this, but I trust you guys can pick this up pretty fast. The final thing we're going to look at in this notebook is TensorFlow variables. Basically, variables can be thought of as like, so in TensorFlow, every tensor object is immutable, right? So you can't do, we've had questions in the past where people say, hey, can I create like a cycle in my graph where it says, hey, like I'm going to take node A, and with this tensor, it's going to have some input, and then the next node's going to depend on that A. This one's so B depends on A, then we're going to say C depends on B, and then we'll try to go back and say, hey, I want to make A depend on C again. You can't do that. Basically, if you tried to do that, you'd just be creating more nodes and assigning the new node. You'd just be replacing the handle to the original node with handle to the new, like, fake A up here. But we do have the ability to have state in TensorFlow, and the way you do that is with TensorFlow variables. TensorFlow variables are going to be what you use when you are training weights, because those are what are going to get incremental changes over time to be able to actually change your model. The basic way to define TensorFlow variables is with the tf.variable, capital variable. We can start this at 0. We'll give it a name because we're good. We're good citizens. And then what you need to do, like I said, the placement of variables is in charge of the graph. Or the graph is in charge of where the variable is placed and what depends on it. But the session is what's in charge of the actual variable. We're passing in this 0 here. But what this value is, this 0 doesn't say, hey, this variable now has the value 0 when we start it. Rather, it's saying, hey, the default value for this when this variable is initialized should be 0. So when the way we actually initialize them, you can do initialize variable and pass in a handle to the variable, but the more common thing to do is tf.initialize all variables. So when you do that, it will actually give the value of my variable the value 0, and now we can actually run it. So if we wanted to, we could actually now, let's go back and we're going to reset this so that we can see what happens if you try to run a session without a variable. So we do session, and then if I try to do session.run my var, right? We try to do this, like ideally, we think, oh, we just get the value 0. Instead, we get this, hey, this isn't initialized, attempting to use uninitialized value. So we're not going to do that because it makes it unhappy. Instead, we're going to initialize it first. And then we can actually, if we were to run session.run my var, then we actually get the value 0 without any errors. So now down here we can actually use create an operation that actually increments this variable over time. So we can say, hey, I want to create this increment operation which is reusable, and that increment operation is incrementing my variable by 1, right? It's itself plus 1 number. So if we do that, we'll see that we're going to get this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But because it's a persistent variable, if you run it again, you'll start from 11, and then if you do it again, you'll keep going, right? So that's the basic idea. You have these persistent variables that keep their state over multiple graph runs. When you do initialize all variables, it'll actually reset that. So if we run this, if we do initialize all variables first and then run this increment variable again, we'll just get 1 through 10 once again. There are one important parameter that can go into the variable initialization, right, is the trainable. It's a Boolean value, so you can say trainable equals true or trainable equals false. By default, it's true. Basically, there are features in TensorFlow that allow for basically automatically do gradient descent for you. And the way it works is it says, hey, if this variable was used in this gradient descent, I'm going to tweak the variables for you without you having to go and explicitly define each weight that you want to tweak. So if you want to have something that is like a step counter for how many steps you've done, you should say, hey, I'm going to set the training explicitly to trainable explicitly to false, so that the only time it changes is when I, the user, explicitly run code to adjust the value of the variable. The other thing you should know about, there is this get variable function. In general, the preferred way to get and use TensorFlow variables is with this get variable command. Essentially, it allows you to do specific things with variable scope, and basically it makes sharing variables a lot more easy and you have a lot more control over it. Whereas if you use tf.variable, things can get kind of hairy when you have more complex models. When you're doing your basic stuff and what we're doing with today, it's not a big deal, but tf.getVariable offers you more security and more power to make sure that you're not accidentally doing something stupid when you're doing that. There's an official how-to on how to use that and how to deal with variable scope. It takes a little bit of getting used to if you're used to just freewheeling with the tf.variable command, but it's definitely worth learning how to do. So that's the the basic outline of TensorFlow. I know it's a lot of very dry material, but I want to make sure that we're all on the same page. Are there any questions about basic TensorFlow stuff before we move on to the actual models? How are we doing?
Is it 5:20?
Yeah, 5:20.
They might kick us out, that's the only thing.
What's the time for everything?
I'm scared of that guy.
Well, what time do we have it till?
Yeah, 5, I think.
Oh, okay. Well, let's sprint through this. So quickly, let's open up our. We're going to open up both feedforward and the CNN, convolutional neural networks, guys. And just for the sake of saving your own processing, click checkmark your TensorFlow fundamentals notebook and click the shutdown button so that we don't have all this extra random TensorFlow sessions running in the background. So quickly, I'm going to try to run through this as fast as possible before we get kicked out. I have the same TensorBoard, and I'm going to be running these. I have the same TensorBoard helpers that I had from before, right? Those are all really nice. We import TensorFlow. Then we have these extra little helpers to help us do some data manipulation. So we've got this, we've included this not MNIST data set. If you guys are familiar with MNIST, this is not MNIST. It's basically, instead of handwritten variables, it's a collection of weird fonts and other shenanigans to use as training data. So we can, this basically just says, hey, we're going to set this data set directory, our data set directory as this already pre-downloaded not MNIST set. Then we have a couple of helper functions that's like, hey, maybe I need to download this file, maybe I don't. Maybe if it comes in as a zip file, so if it exists, don't extract it. If it doesn't exist, extract it. That defines those variables. This is the location of those variables, right? And then we have these downloading the two data sets, right? So this will maybe, like the first one, will download the small one, and then we're going to extract the folders if they don't exist. So it shouldn't take too long if the data isn't already there, right? Luckily, it's the small ones, so we're not dealing with that too much. So this is just going to go through, and once it's done, you won't have an asterisk here, and you'll see that we have the letters A through J somewhere in our directory structure that we've already defined. We can take the length of the directories just to see how many different labels we have. A through J is 10 different letters. Now we start getting into some of the image manipulation. Again, sorry for sprinting through this, but basically we have to do some manipulation, make sure that our images are in a nice format for TensorFlow. And this is mainly done with NumPy. So basically we have this, because we have it listed in folders and we need to bring it in as a data set, we're going to define some functions that allow, like basically go through, scan through and say, hey, I need you to go into this folder, collect all the images, put them into this, shape, array shape, essentially. So that's what that function does. And then these are different ways to basically attach labels to each. Like we have a function that attaches the correct label. So A is 0, B is 1, etc. J is 9. We have one that splits off data into a training and a test data set. I didn't bother with a validation set in this one just because it's a simple example. Normally you'd have a trained data set, a validation set, and a test data set. But for the sake here, it's just splitting it up into different components. And then basically we're saying, hey, can you please set up our test data sets and our trained data sets? That's what these two are. So once you get these running, you should see some of these. Basically has some features in there that say, hey, if you get an error when trying to read an image, just skip it and move on. Don't worry about it. Once those are done, you shouldn't see an asterisk here. They should be good. And then we can take a look, see the length of our training data set, and it's about 17,000. Now we're going to start moving these into flattened vectors. So these are, I think, 28 by 28 pixel images, or either that or 18 by 18. I can't remember the exact dimensions. Basically, we have them as a square set of pixels. We want to convert that into a longer single vector, if that makes sense. So we're going to be reshaping that, and that's what these are. These pictures are grayscale, so we're keeping the num channels like that. And then we reformat our train set and our label set, our test and training sets, both their labels and their datas, to be in that format, basically a vector instead of a square matrix. So now once we print that out, you'll see, okay, we have this many. The first one is the number of examples. So we have 17,000 training examples, and each one of those has 784 pixels as a vector. Now that's what we're seeing here. And then this is our labels. So we have the same. These obviously match. We have the same number of training example or input examples as we do labels. It's just that now instead of 780 pixels, we have one of the 10-letter labels that we had, and then we have the smaller test set from before. Next, we have the shuffling function that allows us to actually shuffle the data around in a nice way. That's just basically good data practice, right? We want to make sure that everything's shuffled effectively. And then we have our shuffling with the labels. That basically it's a helper to make sure that the labels, when we shuffle, the labels stay attached properly. And so now, finally, we're actually getting to our real model in TensorFlow. So as you guys are aware, like if you weren't aware before, data science is a lot of cleaning data before actually making the full model. Now we're making the full model. So let's just go over what we have here. So basically, we're going to create a simple feed-forward neural network with 300 layers in the first hidden layer, or 300 nodes, I should say, 150 nodes in the second layer, and then 50 nodes in the third hidden layer before outputting our 1 of 10 outputs. We're going to have 64 examples per batch. So we're going to, before making any tweaks to our model, we're going to have it look at 64 images and make a prediction on each of those models, and then accumulate gradients that way. So that's that. So now we have to make an input, like basically say, hey, I need to, for each example, we're going to need to put in the input data, which is this, and we're also going to need the labels for the input. You can see here we have this shape with the none that allows us to basically say, hey, instead of, we could decide to make this 128 if we wanted to, and because this is none, it's not hard coded, right? It allows it to be more flexible. So we have these input labels, and then you'll see these tf.namescope, or the namescope variables. That's all that is a little nicety to help group your code together, and you can take advantage of the visualization in TensorBoard. So basically we're saying, hey, this is our first hidden layer. What we're doing is we're defining our weights to be a variable, right? It's a matrix variable. So it's the image height times image width, which was our 784 vector length that we saw before, times the number of hidden units in the second layer. If you're not comfortable with matrix math, it's okay. Just know that basically we need our matrices to match up. So we have a 784 vector from your guys' perspective here, and then we need to transfer that into a 300-dimensional vector, essentially. So the way we do that is with a 784 by 300 matrix. So that's what this weight here is. And then we have these biases that are also a variable that we'll be able to just add in naturally. Then the activation function that we're using is sigmoid. I know it's out of fashion, but I just figured to keep it simple and easy for this example. So what we have is these are so-called, like, I guess they're not logits because we're not passing it into a logistic function. I guess we are passing it a logistic function. These are our logits. And so we basically do a matrix multiplication on these guys, which will end up with a vector of length 300. And then this bias is another vector of length 300. Num hidden 1 is 300 here. So when you do a vector addition like this, it just does an element-wide addition on all these. So the net result is effectively your WX plus B bias. And that gives us the hidden 1.
Is it possible to design activation functions and insert those for the...
Yes, so can we design our own activation function? So you can, if you want to create, there's a number of activation functions that are available. Just off the bat, you have 10H, you have all sorts of things. If you want to, you can create a function that basically, if you want to compose an activation function that is a composition of available functions inside of TensorFlow, that's pretty simple because all it's going to do is go back and back-propagate through all of the transformations that you do with that. If you want to do something that is completely not in the TensorFlow library, yes, you can define it, but you have to implement it in C++ and then go through some extra overhead to actually register that custom code yourself. There's a how-to in the TensorFlow documentation on writing your own operations if you wanted to do that. Yeah.
So back propagation works for all the application functions that you have.
Yes, yes.
If I define the I have to define.
You need to define the gradient. Yes, exactly. And that's also part of the operations. So in this one, then if you're familiar with like a feed-forward neural network, we just do that again and again, basically. Same idea, just with slightly different dimensions for our weights and biases. Until we get to our output layer, at which point we're going to be essentially, we go through, and finally get the logits, which are, again, this just input here. And instead of doing a sigmoid function or a logistic function, we're going to be using a softmax function with cross entropy error, and that's what this function is. And then, because just to even things out, we're going to reduce the mean of that, so it doesn't. Basically, we don't have to have bigger error if our batch size is big or small, right? It's just we want to make it seem a batch size of 1 should have about the same effect as something that has a batch size of 64. It's just that our bias is different, right, for those. That's what reduced mean does. It just takes the mean of our cross entropy error. Then we take this loss and pass it into our our basic gradient descent optimizer. This is basically your the function and object that allows you to automatically perform gradient descent. There's ones for atom and adagrad and different types of gradient descent. In this case, we're just doing basic gradient descent optimization. The value that we're passing in here is our training rate, is our learning rate. And right now I'm just hard coding it as 0.05. You can actually make this a placeholder, and then you can by hand put in the exact training rate that you want to have for each run. There's also options to have naturally exponentially decaying learning rates and all that. And then, so this gradient descent optimizer is an object, and then we have this minimization method that returns the op to actually do that. Okay, almost done. Then in order to actually create a prediction, we're going to have the softmax of our logits, and then we're going to pick whichever number is highest in our model prediction, make that value 1, and then make everything else 0. Basically make a one-hot encoding out of our prediction logits. And then we have this scalar summaries for extra things. In any case, now then we merge the summaries together. That allows us to basically say, instead of by hand saying, hey, give me this summary and this summary and this summary, you can merge them all together and say, hey, give me all the summaries, please. So right now, all this is right now is just define. Remember, we define the graph first, and then we're going to run the sessions later. So we'll be able to say we'll be able to do that once we get to the session running here. So once you run this code, you have the graph defined. I clean out this just deletes the TensorBoard directory just so that we don't accidentally have it. Then we start up a session, and this is where you can actually think about the epochs. In this case, it's going to go through several epochs because we have 17,000 examples, and then we're going to be doing 1,001 steps. So since our batch size is 64, we'll go through 64,000 switches, and you can do things to keep track of your own epochs and all that. So we start up a session, we start up a writer, we define the session, we have some logic in here to help you basically go through the code. I don't think I have any shuffling of the training data after each epoch, but normally you would have that. This is basically just code that says, hey, go to the end of the training set, and then once you get to the end, loop back around, like that. So once we actually run this, you'll see that we're actually going through and outputting some accuracy at each step. And this is creating this basic neural network model, and after that we get like 70%, which is crappy, but it's a simple feed-forward neural network. We can close it. We can close I'm retraining it accidentally. It'll only take another second. We can then close our summary writer. We can start TensorBoard if we want to look at our results in our training set. So if we go to your address pipeline, that's just 606. Eventually it'll pop up. We can have our accuracy and our loss, and because I need to clean out the TensorBoard directory, that's why I'm seeing these multiple things here. I ran multiple. But you can see that our loss is going down and our accuracy is going up over time. If you look at our graph, you can see that we have these name scopes, right? So I mentioned these name scopes are useful for TensorBoard maneuvering. You can see that just by having these in here, you can actually separate and check out your graph in more an easier way. And then you can also have your summaries in their own separate area. You can have the gradient descent optimizer automatically creates its own name scope over here. And these are the gradient functions, right? The gradient operations are built into TensorFlow and are separate from the original gradients. when you go through and use gradient descent, it's going to say, hey, I need to place these gradient operations in the graph for you and run those automatically. So that's what this gradients area is. This is gradients for like matrix multiplication gradient, the gradient of the add operation, etc. So yeah, so that's like the first thing, and then I think there's a little sample where you can actually go through and take a look at some of the visualizations with matplotlib. So this can go through and say, hey, our model is predicting a D, it's actually a B. It's like, oh, that sucks. It's wrong. It's like, oh, this has got an A. Hooray, I got it right. And according to before, it's about a 70% accuracy rate, right? But this is just some quick data. Yeah, it's like, whoops, wrong. This is correct, right? But again, simple feed forward neural network. I don't have time to talk about convolutions, but just for the sake of going through and seeing that it's better, you can go to the CNN one. Basically, just click all the way through. We're going to just run all these, and eventually we're going to have, instead of it running before, we're having this different model that it takes a little bit more time for each example. But you can already see that we're starting to get better and better accuracy because we're using convolutions. As this is training, the basic idea of a convolutional kernel is that instead of looking at each pixel independently, what we're doing is taking a look at each pixel and its neighbors, and then seeing if there's any localized data to that, and then squeezing it down into a different vector space, right? And so if you do that over multiple layers, you end up extracting more meaningful features. So if you've seen examples where people say, oh, if you look at this layer in this this neuron, you can see it's detecting edges, right? It's detecting horizontal edges. The convolution, like these kernels, right, allow you to get those sorts of features, right? And there's different types of kernels that you can use. But again, unfortunately, I don't have time to go over the math and the specifics here. Just know that you look at the end here, the test accuracy, which was at 70% for, is now up by 20%, which is pretty good for just 30 seconds of training. We can go through and like, no, accidentally running again. It'll just take another 30 seconds to go. And then we'll close the writer. Then we can start up TensorBoard and see the different model. There won't be a huge difference in what it looks like in TensorBoard, but you can go in and explore what the actual differences are. And then we'll just finish up by doing the visualizations and patting ourselves on the back that our model is better than the past one that sucked. So now that I have started this new one on 6006, if I restart this, we should theoretically get the new ones. You can see we now have this more intense graph summary, right? If we go in here, we'll see that we have dropout functions in here. We'll have rectified linear unit things instead of our basic sigmoid functions. We have these two-dimensional convolution kernels. That's all fun for exploration. But now, at the very end, we'll close down our TensorBoard, and now let's actually see what it's not going to be perfect, but it's going to be better. C, awesome. No, but I guess it doesn't look like a J at all. Terrible. G, H. What? In any case, I mean, it's not perfect. What? Bad luck. In any case, there we go. Getting a couple in a row. So again, it's still, this model obviously is hardly perfect. It's just a very simple model designed to run on this model is actually designed to just lightweight, small scale, something that you can run on your laptop, on your CPU without needing this massive image that we have. But you can see that just by just a few minutes of your time, you can already create something that can do basic image recognition tasks. And just by adding in, learning a little bit more about the framework, learning some different model architectures, you can start getting things that are really damn useful without too much computational power. And then, of course, when you want the computational power, you have the option there as well. I don't have time to talk about how we're planning on incorporating TensorFlow into pipeline, but basically we're hoping on utilizing TensorFlow Serving and online training techniques to basically create a nice system for automatically training creating a nice pipeline for automatically training models live, and then being able to do A/B testing and multi-arm bandit testing to be able to hot swap in your live models. So you have basically a separate training feature, and then you have a series of live models. Then, like with a little manager in the middle, being able to communicate, hey, we have a new model. Let's see whether or not it's any better than what we currently are running. And if it is better, then we can hot swap those models in without any downtime on the deployment side. So that's one of the goals that we're doing with TensorFlow and Pipeline.io. Thank you for listening to my little TensorBoard talk. Yes, sir.
Can you please comment on TensorFlow's distributed computing?
Yeah. So when TensorFlow first came out, one of the most exciting things one of the things that people were most excited about with TensorFlow was this distributed capability, because it came out and said, yeah, TensorFlow, it's going to be, you can put it into production and you can do it like it's distributed and it's going to be great. And then, people looked into it and it's like, well, the open source implementation doesn't have it quite yet. But earlier this year, in February, the first portions of the distributed framework were put out, as well as the TensorFlow Serving software that allows you to actually put things into production. Currently, TensorFlow distributed is functional and totally works. The annoying thing is that it's still like a little bit less user-friendly than you would hope. Granted, most distributed training situations aren't particularly user-friendly. The main thing is that right now you either have to enter your cluster specification by hand, like which you have to say, oh, it's going to be at this IP address at this port, right, by hand. You can also start up those servers by hand, or you have to string together your own logic to do that for you. The hope is that by the end of the year, what my fingers crossed, is to have native Kubernetes support to be able to start up your own containers, right, and have that managed for you. Have the information for where variable like parameters are being hosted, as well as just which ones are worker servers. Have that coordinated for you through Kubernetes. That they're focusing mainly on Kubernetes because Google. But that's code that is in the works. In the GitHub repository, you can find snippets of code that reference, like, not just, we want to add Kubernetes, but actual logic and placeholder stuff for Kubernetes. So it's not perfect right now, and it's evolving, and I don't want to like start teaching you how to do all this really hard, complicated by hand stuff if they're planning on having it be a lot more user-friendly in the next couple of months. So if you want to start experimenting with it, by all means go for it. It's super fun to play around with. There's the simple distributed TensorFlow tutorial on their site, but that one isn't as good. Like, that one is helpful to get you started, but there's some information missing. There's actually a training the inception model tutorial that does it on a distributed setting, and that's going to be super valuable for you to understand exactly what is going on in terms of setting up a distributed cluster.
What tutorial was that?
So there's a training inception model. So let's see if I can get that.
It's part of the.
Yeah, these are all official tutorials that I'm bringing up here.
No, but it's part of Flux.
Oh, it's in the Flux. Oh, nice.
Yeah,
So we have that.
and it uses distributed TensorFlow.
Yes. So if we go to, actually I'm not sure about yours.
Sorry.
Training inception, TensorFlow.
The Flux stuff is just TensorFlow Serving, the inception stuff.
Yeah, so TensorFlow /
Stupid question.
Yes, sir.
TensorFlow Serving and distributed TensorFlow, can you do serving on distributed TensorFlow?
So basically right now, the idea is yes, right? Because basically what TensorFlow Serving does is it takes your existing model your specification code and just puts that into serving. The thing is, it's just, right now it's a little wonky and not, it's just, in theory, yes, but it's just, it's something that I need to play around with more to be able to get a better grip on it,
I
right?
guess do you put your cluster spec into your code?
Exactly.
If you're still going to be serving it.
Yeah, exactly. So the TensorFlow Serving code the thing there is that if you want to have multiple versions of your code, right, because it's sort of hard code, you either have to change your parameter specifications for each serving model, or each container with your serving model will communicate with the same worker nodes, right? So it's just something where it's like, but TensorFlow Serving will automatically take advantage of the GPUs that you have on your machine, right? And all of that. But the short answer, yes, it does. Long answer, like, it's more complicated. But if you want to do your distributed, just to show you where this is, github.com/tensorflow/models/tree/master/inception. I think maybe tensorflow.org/model/inception will also do it. But basically, this is like, this whole thing is a distributed training TensorFlow tutorial. It just happens to use the gigantic TensorFlow Inception model, but it's going to be a really good way for you to sort of see the patterns that the Google people actually use to set up this this model. So yeah, one more question. Sorry.
How do we incorporate online training in TensorFlow?
So basically, online training right now, like, that isn't like something that is actively developed by the TensorFlow team. The thing is, because TensorFlow sessions and the variables are all live while your code is live, you can actually set up something like, just for like the simplest case, you can think of just starting up a Flask server and just say, hey, I'm going to have this TensorFlow graph running in this code, and it's going to stay live while I have my Flask server running. And you can say, oh, when somebody makes a GET request, I'm going to run this session. Like, I'm going to run this graph with the live session with the data that's coming in, and it will continually train the model. But again, that isn't something that's native to TensorFlow. That's something that that's a task that we're trying to work on right now. But the one basic idea is saying, okay, Python, like, this Python information is live. There's no you can basically treat it like any other sort of stateful code.
The session needs to be alive always.
So it's something where you can. So there's a couple of things that we can do. One, you can that I haven't mentioned for this, right? One, you can output your model periodically, so you can save different versions of your model over time. And then, as long as you have the code running, like, when you can have, if you had this, if you just had a line that said, like, my global var equals 0, right? And then you had started a Flask server, a Flask application underneath that, and then had a REST call built into that, you can actually update that my persistent variable, right? And it will stay alive, right? It's not going to close until you stop the Flask server, if that makes sense, right? So that's one basic way that you can implement that. But we're going to see if we can dig deeper into the C++ implementation. Yes, sir.
Can you export your TensorFlow graph into PMML?
So that's something that we've actually also been looking at. The thing is, it's easier to imagine going from PMML to automatically making a TensorFlow graph. It's like, this is something where basically I'm relatively new to PMML, right? So it's just something where it's not built into TensorFlow. We're looking into the options for that sort of thing because it's growing. Yes, sir.
So, for TensorFlow, there's a high-level interface for the physical learn. So do you envision that would be the major usage pattern for the common user? That's not easy to use.
Yeah, I think. Well, it's like, I think there's a lot of people are going to find we mentioned there's tf.learn, right? So there was this library, the TensorFlow Learn, scikit-learn. It mimics the scikit-learn library, and there's also another one that has you can do layer by layer definitions. It's a little bit higher level, and it's a little bit less nitty-gritty doing matrix multiplications. Yeah, I think that's a really great way to use TensorFlow. But for me, I think just when you're learning TensorFlow, it's important to get the slow stuff out of the way so that you know what is actually happening under the scenes. It's just something where TensorFlow by itself is designed to be this very flexible mathematical computation engine, and those the layer by layer definition may not give you the flexibility that you need if you need to plug in an extra component up here, right, that has a novel computation design, if that makes sense. But yeah, I think that tf.learn and the layers, the built-in layers API is good. I think that Keras, which runs on either TensorFlow or Theano, is also very good. With both of those, you can always tap into the lower level stuff through their APIs, and then you can have access to the things we talked about today. But yeah, the answer is yes, and by all means use that if you would rather be doing that, because it can save you time. Unfortunately, I think it's time for us to skedaddle. But thank you guys so much for coming out. Thank you for sticking with us.
Yeah, guys, this is why we live in this area, right? We can share knowledge. So thanks for coming.